Hi everyone. In this video I'm going to talk about some initial proofs with relations. To start us off, I want to look at a proof that has nothing to do with the relations, but I thought it might be interesting to you. This is a proof from Sherlock Holmes that 1 equals 2. So A equals B. Multiply both sides by B, you get AB equals B squared. So then you can subtract A squared from each side. Factor out an A, so you get A times B minus A equals, and factor this side, difference of squares. Canceling out the A minus B on each side leaves you with A equals B plus A, but A equals B, remember. So A equals 2A, divide out A, and so 1 equals 2. See if you can find the flaw in that one. Alright. We're going to do some initial proofs with relations. And before we do that, I just want to review a little bit about relations. Relation is a set of ordered pairs. It consists of a domain and a range. So if R is in the subset of A cross B, that means the first element, remember R is a set of relations, x, y. X comes from the set A, y comes from the set B. May or may not, it's a subset, may or may not consist of all of A and all of B, but at least parts of it. The inverse of a relation, R, so it's R inverse. R inverse is a set of all yx's in B cross A, where x, y is in the relation. So, if x, y is in the relation, as we said in the last video, if 1, 2 is in the relation, then we know that 2, 1 is in the inverse of the relation. Two symmetry definitions will be helpful. We said that R is a symmetric relation if and only if, if xy is in R, then yx also has to be in R. That would make it symmetric. Also, it's symmetric if the inverse, R inverse, is equal to the initial relation. Alright, so let's look at we're going to look at a couple proofs similar to what I've asked you to do on homework. And these are proofs of what we're going to call our initial relation properties. On page 112 of the Fletcher and Patty book, proposition 4.3 lists 6 initial properties of relations. Relation R is equal to R inverse inverse. R is a subset of S if and only if R inverse is a subset of S. That's kind of a tough one to prove. If and only if means you've got 2 things to do. And here are 4 others. For your homework, you have to prove D and E. So I'm going to do 2 of them, and they're similar. I'm going to prove C and F. Okay. Part C, this is proposition 4.3, says that R union S inverse equals R inverse union S inverse. That sort of throws a few people, because I know with sets it's when you take the negation or the complement, R union S complement would be R complement intersect S complement. But with the relations and inverses, it doesn't quite work the same. So here's the proof. To prove that sets are equal, we have to prove 2 things. We have to prove that side 1 is a subset of side 2, and vice versa. So, to prove R union S is a subset of R inverse union S inverse, let's first start out by assuming that we have some element xy that's in the first part. So xy is in R union S. By the definition of the inverse, then, we know that yx is in R union S. So, if xy is in the inverse, then yx has to be in the initial relation. Oh, but by the definition of union, then, we know that yx is in R union S, so that says that yx is in R, or yx is in S. But if yx is in R, we know that xy is in R inverse. And that's the basic relation you've got to keep in mind. You know that if that's the definition of the inverse. If xy is in a relation, then yx is in its inverse. So we have xy is in R inverse, or xy is in S, but that would say that by the definition of union, that xy is in R inverse union S inverse. So what we've shown is that xy is in R union S inverse implies that xy is in R inverse union S inverse, so R union S inverse is a subset of R inverse union S inverse. Now that's half the proof. Here's the second part. We've got to prove that R inverse union S inverse, in other words, we want to prove that the second side, let me go back to my pen, is a subset of the first side. So again, to do that, you have to assume you have some element xy in R inverse union S inverse. By the definition of union, that would say that xy is in R inverse, or xy is in S inverse. Oh, but then by the definition of inverse, if xy is in R inverse, then we know that yx is in R. So if xy is in S inverse, then yx is in S. So we have that yx is in R, or yx is an element of S. So that says, by the definition of union, that yx is an element of R union S. Then, by the definition of inverse, if yx is in R union S, then xy is in R union S inverse. So what we've shown is that xy is in R inverse union S inverse implies that xy, the element, is also in R union S inverse. So that says that R inverse union S inverse is a subset of R union S quantity inverse. So overall, since side 1 is a subset of side 2 is a subset of side 1, R union S inverse and is equal to R inverse union S inverse. Okay, let's look at the second homework and homework-like problem, similar. The statement says, and this is proposition 4.3f, that R intersected with R inverse is a symmetric relation, regardless of relations R and R is. So R intersect R inverse is always a symmetric relation. So I'm going to actually show you two proofs of this. You can choose whichever one you like. So S is symmetric. This is a definition. If and only if xy is in S, then yx is in S as well. That's definition 1 of symmetry. So if we want to prove that R intersect R inverse is symmetric, let's start out with some element xy in R and intersect R inverse. By the definition of intersection, we know that xy is in R and xy is in R inverse. That's what it means to be in the intersection of R and R inverse. Oh, but by the definition of inverse then, we know that yx is in R inverse and yx is in R. Oh, but then going back to the definition of intersection, we know that yx has to be in R intersect R inverse. So what we've shown is that if xy is in R intersect R inverse, that means that yx is also in R intersect R inverse. So by the first definition of symmetry, R intersect R inverse is symmetric. Now, here is a second proof of this same statement. And it uses a second definition of symmetry. And again, this is sort of the old adage. If you know how to do a problem one way, that's great. If you know how to do it two ways, that's even better. So the second definition of symmetry says that a relation S is symmetric. Let me get a different color here. relation S is symmetric if S inverse is equal to itself. So to do this proof, we're going to use other properties from proposition 4.3 and one way back from proposition 2.5 when we introduced sets. We want to show that S inverse equals S. So let's see what S in this case is our R intersect R inverse. So what we want to do is, if we show that symmetric, we want to show that R intersect R inverse is equal to R intersect R inverse. In other words, think of it as blob inverse is equal to blob. So R intersect R inverse. By proposition 4.3d, that says that, which is the one we just proved, then that expression equals R inverse intersected with R inverse inverse. In other words, you don't really distribute, but you can think of it. That's R inverse inverse. Oh, in proposition 2.5 and sets 2.5d, we know that intersection is commutative. So I'm just going to switch the order of these two things. The statement in 2.5d says that A intersect B equals B intersect A. So R inverse intersected with R inverse inverse is equal to R inverse inverse intersected with R inverse. Just switch those two sides. Finally, by proposition 4.3a, R inverse inverse is equal to just R. So this expression equals R intersected with R inverse. So what we've shown is that R intersect R inverse equals itself, R intersect R inverse. In other words, again, blob inverse equals blob. So because that's true, we know that, I don't know why I have two here, just still cut and paste error. Cut that one out. We know that R intersect R inverse is a symmetric relation.